Hello, everybody. Thank you for the invitation. And I will report about free electron laser from its origin to recent developments. So I like to introduce free electron laser using the words of Charlie Brau, who wrote the first book on free electron laser. And he said that it uses a simple and elegant gain medium, which consists of an electron beam in a magnetic field. So this is indeed a very simple device from that point of view. So such a gain medium provides a broad wavelength tunability, and the vibration frequency can be adjusted by changing the magnetic field or the speed of the electrons to the difference to bound electrons in atoms and molecules that do vibrate at specific frequencies. And such a free electron lasers also provides an excellent optical beam quality and can provide high power. So I would like first to explain you how the idea of free electron laser emerged. And it comes from synchrotron radiation development, vacuum tube developments, and laser developments. So to introduce about the vacuum tubes, we come back to relativity, and I do consider an electron of electron energy E, and which has a relativistic factor gamma, which is E over the rest mass, multiplied by the speed of light square. Then we can introduce a normalized velocity, and the relationship between the normalized velocity beta and gamma. So we make the approximation of ultra-relativistic beam, and we have the beta along the S trajectory, which is the main trajectory of the movement of the electron, which can be approximated like this. And then for vacuum tubes, these electrons are submitted to electric and magnetic field, so we do apply the Lorentz force. So I will start with an example of vacuum tube, which is a klystron, which consists of two cavities. So we have electrons which are emitted by a cathode here, and then they enter a first RF resonator where we have an electric field which oscillates at a length delta S and at a frequency nu. With a frequency typically in the gigahertz. So then we can have a gain, an energy exchange, and we write the work. So we have delta W1, which is given by this relationship. So we see that the sign of delta W1 depends on the moment when the electrons arrives inside the cavity. And delta W1 is modulated with a temporal period T and or a spatial period lambda over beta. So in average, this work is 0 since the electrons have different phase. Then, I'm not good with this pointer. Then the electrons enter a drift space, a drift section that you see here, and they accumulate in bunches because some electrons have gained some energy and go in front, and some has lost energy and go in the back. So we introduce here the concept of bunching, and then the electrons enter the second cavity, and the electrons have the same phase with respect to the electromagnetic wave since they are bunched. So we have a second energy exchange, which is then non-zero, and the phase of the electrons is ruled by the cavity itself, and we can have a very high gain. So you see here that the concept of bunching is very important. that we have used resonant cavities at the frequency of the emitted wavelengths, and we can have an efficient retroaction to provide amplification, and we can put loops to have wideband amplifiers. So this concept of vacuum tubes has been used last century as well for developing accelerators. So we have an electron gun, which is like with a cathode, which are emitting electrons. And then we do bunching in a subharmonic buncher. And then we can have accelerating section with an electric field, which can raise the energy of the electrons. So typically we can deal with a linear accelerator, so we have a gun. We can have a harmonic cavity for doing this bunching. Sometimes we do compression chicane. It's like in optics when you do compression pulse shortening with gratings. And then we can have a triplet to do the proper focusing, so quadruples, which are magnetic lenses. And then we have the accelerating sections. And then we can put some other systems. Or we can use a storage ring where we do recirculate the electrons. So some electrons lose energy by emitting synchrotron radiation, and this energy loss is catch up by the radio frequency cavity, which gives back the energy which has been lost. Or we can combine these two types of accelerators on energy recovery linacs, where we do a single pass and the electrons give back the energy to the RF field, and then it's accelerated again. So we have also synchrotron radiation, which emerged last century. So it is electromagnetic radiation produced by charged accelerated particles. So there have been the development of first ideas, some prediction of time dilatation, then first correct calculation of the emitted power, then the angular and spectral distribution, then the energy which is obtainable, then the fact that we have a peak spectrum, and first measurement of synchrotron radiation in 1947 on a particle accelerator. Actually, synchrotron radiation can also be produced naturally, and I put here an example of the sun where we have hydrogen loops of magnetic field which provides visible synchrotron radiation. So now on accelerators, we produce synchrotron radiation with a curved trajectory in a bending magnet, and we have a very collimated synchrotron radiation, which is emitted over an angle of 1/gamma, or we can install a specific device that we call ondulator, which provides a periodic permanent magnetic field. Actually, we put a series of dipoles to emit more synchrotron radiation because we have more curvatures of the trajectory. So the first idea on the ondulator was put by Russians, and then the development of the detailed calculation of the ondulator was done by Motz, and then he made an experiment to see how was this radiation, and he could measure the influence of bunching and observe polarized visible radiation from an ondulator installed on 100 MeV Stanford accelerator. So in France, since we are in Saint-Étienne, I report also about French research. There was Combe and Frollo who worked on this, and they could observe also synchrotron radiation from a 2.3 MeV accelerator. And their result was reported by Louis de Breuil at the French Academy of Science. So you see that people were connected, and people doing quantum mechanics were interested by this development on synchrotron radiation. So then if I go into more details about the undulator radiation, here I do consider a planar undulator, which is producing a vertical sinusoidal magnetic field. Then we can introduce the deflection parameter, and we can calculate the trajectory. So we have here the velocity. So you see that it's the longitudinal velocity that we have this term, which is evolving with a sinus square with a wave number of the undulator Ku and longitudinal position. And then we can also have helical undulators where we have a vertical and horizontal field created both together with a dephasing between them. And if we are in the circular case, then you see that for the velocity, we don't have anymore this oscillating term for the longitudinal position. So about the radiation, so we have this sinusoidal trajectory in the horizontal plane for a planar undulator. And we have the emission of synchrotron radiation at each curvature of the trajectory. So we can have a resonance condition for the wavelengths for which one electron radiation constructively interferes. So I then write that the path difference between the two rays equal n is an integer, and lambda n. So I have here the path for the electrons, and here the path of the photons. I write that it's equal to n lambda, and then I obtain this relationship with some mathematics considering small angles, because synchrotron radiation is emitted ahead. You remember that I told you that the angle is 1/gamma, and then I made this approximation of very rapid electrons. Then I end up with such a relationship. So we have the resonant wavelengths for the harmonic of order n, which depends on the undulator period, lambda u, the deflection parameter Ku, which is proportional to the peak field, and lambda u. So I put in red when it relates to the undulator field, in green when it relates to the electron beam. So the wavelength depends as the inverse of the square of the electron beam energy. So from this relationship, we see that we can tune the wavelengths either in changing the magnetic field strength or in changing the electron beam energy. And then if I look off axis, I have this gamma square, theta square term that we will detail later. We can also find these wavelengths, resonant wavelengths, by doing the Lorentz transformation from electron frame to observer frame and so on. So I am working at SOLEIL. I am the head of the magnet and insertion device group, so of undulator group. So we have built a series of undulator of different periods and different magnetic fields, which enables to cover on such a ring up to 6 decades for the radiation. So you see that for high electron, for high photon energy, we use a short period high field undulator, and for UV region, we use a large period of undulator. The period is given here in millimeter. So concerning the off-axis radiation, then here I put pictures of the first ring on which I work, because the vacuum chamber was rather large. Then we can see well the radiation. So here the fundamental is in the green, and then we have the off-axis radiation, which is redshifted because of this term. So I have the yellow, the red, and then here I have some blue, which is the off-axis radiation of the harmonics. And here then we change the magnetic field, so we change the fundamental wavelengths. So here we have the off-axis radiation of the fundamental, and here the off-axis radiation of the harmonics. Undulator radiation is also emitted as a spectrum of line. So we have finite numbers of periods for the undulator, which I call NU. So then we have the interference from a train of NU periods. And then we have the radiation, which is emitted as a sinus cardinal. And the line width is given by typically 1 over the number of periods and the harmonic number. Then if we have a normal electron beam, it's not a single electron beam. We have a spread in the energy, a spread in size, and divergence. So we can look at the effect of the finite and the divergence of the electron beam on the radiation. So here I show some simulation for the case of SOLEIL. So here I consider a single electron case. So I have a very thin line width, which bandwidth is given by this relationship. Then I introduce some emittance, which is size and divergence. And this corresponds, in fact, to, it's equivalent to off-axis emission because then the electrons are not, strictly speaking, on the axis of the undulator. So I told you that off-axis electrons leads to a redshift. So it's what we see here. We have this satellite peak, which is redshifted. Then if I put the energy spread, actually, I have electrons of lower and higher energy, so it broadens the lines on both sides and limits the peak intensity. And then if I combine both effects, so emittance and energy spread, you see that starting from my filament electron beam, I have damped the radiation. This is on a harmonic. So what we have for an undulator, a typical undulator of period 20, we have the first harmonic with a homogeneous line width, and in that case, the intensity tends to be proportional to the square of the period of undulator because of this interference effect. But if I take into account the electron beam size, emittance, and energy spread, then the scaling is between a square and linear. It depends of the quality of the electron beam. Then I come back to the other origin of the free electron laser, which is the laser concept. So the stimulated emission was proposed by Einstein when he was looking at the black body radiation, and he could understand about the absorption of a photon by an atom, then the spontaneous emission, and then the stimulated emission, where we have two identical photons which are emitted. At that time, the coherent effects were not seen. And then for the development of the maser, the people knew about the vacuum tubes, and with the development of the quantum mechanics, they thought it would be interesting to replace the amplification of the electron beam by in a cavity like I described for the klystron by stimulated emission in a molecule. So they install an excited molecule in a microwave cavity, which is resonant to the molecule transition frequency. And then the first experiment led to the first maser in 1954 with NH3 molecule. And then the question was how to go to shorter wavelengths because we were limited by the size of the cavity, which were rather big at that time. So then Schwallow and Thoms came with the idea of using an optical resonator with very highly reflecting walls, which would define, in addition, a very small angular aperture. So they were guessing that it would provide a very extremely monochromatic and coherent light. So then they were kind of race to get the first laser operating, and the one who was the first to achieve it was Mine with a ruby laser in 1960. Then if we come back to the seminal paper of Schwallow and Towns, they say that at the end of the paper, as one attempts to extend maser operation towards very short wavelengths, a number of new aspects and problems arise, which require a quantitative reorientation of theoretical discussion and considerable modification of the experimental techniques used. These figures show that maser systems can be expected to operate successively in the infrared, optical, and perhaps UV region, but that unless some radically new approach is found, they cannot be pushed to wavelengths much shorter than those in the ultraviolet region. So then John Mady, who was educated in vacuum tubes at Stanford University, he was considering that Schwallow and Towns' description of maser and lasers coupled to the new understanding of the Gaussian eigenmodes of free space, so in optical resonators, offered a new approach to high-frequency operation that was not constrained by the established limits of the capabilities of electron tubes. So he was considering what could be the free electron radiation mechanism that could fulfill this condition. So then he thought to use high peak current with an electron gun and to have virtual photons generated by a strong periodic magnetic field from an undulator. So then he thought already that it could provide tunability. So the concept that he was considering was Compton scattering with the incident electron, the incident photon, virtual photon with the undulator, and he then made the quantum mechanics approach and calculated with Weizsäcker-Williams approximation what would be the gain, which is a transition rate between diffusion and absorption, the difference of them. So he found some gain, and he found that it's independent of the Planck constant. So maybe we don't need a quantum approach. So the quantum approach is a bit complicated, so I don't put it here in details. And then people started to look at a classical approach. So I make it first simple with hand, and then I will go into details. So in the classical approach, what we have, so we put the gain medium, which is the electron beam, inside the undulator, inside an optical resonator. So then we have an electron beam optical wave interaction, which can lead to an energy exchange between the optical wave and the electrons, as you see here. And then some electrons gain energy to the detriment of the optical wave. So the optical wave can be the store optical, the store synchrotron radiation in the cavity. So some electrons gain energy, some electrons lose energy. So then when they progress along the undulator, they get bunched. So we have set in phase the electrons, the emitters, and then we can produce coherent emission. And then with the multipass operation, we can have light amplification, and saturation can take place because then we are enlarging the energy spread. And we are also decreasing a bit the electron beam energy here because we are taking kinetic energy from the electrons to the optical wave. So at the end, the resonance condition is no more valid. So also the gain scales with electronic density, the cube of the undulator length, and the inverse of the cube of the electron beam energy. So we see that if we want to go to short wavelengths with the resonance condition, we have to use large electron beam energy, but then the gain is very low. So to start with FEL, it's better to start with the infrared, which will be simpler to have gain. So then we can also define two regimes, whether we neglect or not the plasma pulsation. And I will consider only the Compton regime here, where we do neglect this plasma pulsation. So then John Mady, after having found that he can have gain, then I go a bit more detail about the gain process and how we have this free electron laser model. So another way to see about this approach for having gain is to look whether we have a resonance between the electrons and the photons, which is the synchrotron radiation, which is emitted by the electrons and stored into the optical resonator. So we can have a resonance if the wave, when the electron progress by one undulator period lambda u, the wave has traveled by lambda u plus one wavelength of radiation. And then so we can write this, then develop the mathematics, and we find again the same relationship, which is what we found for synchrotron radiation. So we see that the FEL works on the synchrotron radiation wavelengths. So if I go into the details, I first look at the first order energy exchange. So I consider an optical wave of electric field E. And then I do write the work between the electrons and this electric field E. So it's like for the klystron that I have introduced you at the beginning. So then I develop the calculation, and after some mathematics, I can introduce the ponderomotive phase, which depends on the undulator wave number, on the optical wave number, where I have a kind of slow varying term and a rapidly oscillating term, which is related to this twice the undulator wave number that we have for a planar undulator with the longitudinal trajectory. So then I can write the energy exchange like this. And then we look what happens for the resonance. For the resonance, I consider that the electron phase is stationary. And then if I have an optical wave which is resonant to the undulator wavelengths, the work which is applied to the electric field in average is 0. If I am slightly detuned, so I introduce the detuning parameter. So if I am not strictly at the resonant energy, then I can have such an energy exchange, but some electrons, the electrons have different phases. So some electrons are accelerated, some are decelerated. So in average, I have 0 energy exchange at first order. So if I want to see how the bunching takes place, I look at the velocity of the electrons that we have calculated before, and then I can develop this velocity, and then I see that I have a variation of speed which leads to a bunching, what we call velocity bunching, because we do the bunching by different velocities. So if I go to the mathematics, I can develop and find the expression of this benching. So we find that the electronic density is modulated with a period equal to the resonant wavelengths. So it's what I said already, electrons are put in phase, and we have the elementary oscillators which are set in phase, and they could emit coherent radiation. So now we look at the second order energy exchange, because at first order we have 0. So the expression is given here. And it follows this type of function, so which is antisymmetric. And we can find that for the interaction to occur, the wavelengths should be slightly different from the resonant wavelengths. And we find the conditions for amplification and absorption. So we can also see that here we have the spontaneous emission, and this gx function is a derivative of the spontaneous emission, as you see here. And this is known as the Medi theorem, which was used for a while for low-gain for electron laser. So what we have here for the gain depends on the undulator parameters. For a planar undulator, because of this oscillating term in the longitudinal position, it goes with Bessel functions. We have the dependence with the electron beam, so electron beam density and electron beam energy. And we have a sinus cardinal term here, which is due to the phase that we have, to the fact that we have NU periods of the undulator. Of course, for a thick electron beam, we have to introduce some correction due to energy spread and emittance. We have also to have a proper overlap between the electron beam and the photon beam, so we can introduce a correction term, which is a filling factor. And we have also to have a overlap with the longitudinal coordinates, which is a longitudinal overlap. So then for the saturation, we have some energy beam loss, which is due to the energy exchange, and could be due to spontaneous emission, but it's usually negligible. We have then an increase of the energy spread, and also we have the light and the electrons, which are not traveling at the same speed, so we cannot work with infinite undulators, because at some point the light will escape the electron bunch. And if the electron bunch is very short, this can be limiting. So we can also consider the energy exchange, like which is such an expression, and introduce a ponderomotive phase, EP, which is defined by this expression. So it's another way of seeing the phenomenon of electron laser. And we have here, we can look at the phase evolution, the energy evolution. We combine the equation, and we arrive to this equation, which is actually the pendulum equation. So the low gain FEL process can be seen as a pendulum. And for instance, in the community, there is an FEL price. And when you gain the FEL price, you get a pendulum, because it's very the basic of the FEL principle. So what do we have? We find the same thing that I already explained. On resonance, we have no energy transfer, and near resonance, we have energy exchange, and the electrons gather around position for which the energy variation keeps a constant site. So then we have the electrons which can bounce back and forth, and when they do that, it's what we call, they follow synchrotron oscillation. So then John Mady, after developing the gain, he set up a team at Stanford University to try to demonstrate experimentally the free electron laser. So he used Stanford linear accelerator. They built a superconducting ondulator by putting some copper along a tube. So they made a helical ondulator. And first, they tried to verify that the spontaneous the gain is the derivative of the spontaneous emission. So they use an infrared laser that they sent inside the ondulator, and they measured the gain, and indeed it is the derivative of the spontaneous emission. So this is a first remarkable result. And 1 year later, they could observe the FEL in the infrared. So I recall that we started in the infrared because it was easier. So you see spontaneous emission, which starts to be amplified, and the nice line, which is thinner. So this was in 1977. Then in the paper by Deacon, they explained that much hope was put in recirculating machine because at that time, energy spread was smaller than on linear accelerator. So in France, we had the ACO storage ring, and a collaboration was set up between the Stanford group and ACO team. So it was the beginning of synchrotron radiation in France, and Yves Farge and Yves Petrov decided to go on with this collaboration. But actually the gain was very low, and it took 6 years to achieve the free electron laser, and actually the American team was already back to US. So as the gain was very low, an idea which was taken from Novosibirsk was to replace a single ondulator, but what we call an optical klystron, which consists of 2 segments of ondulator with a dispersive section. So the first ondulator, we do the energy exchange. Thanks to this dispersive section, we can do an efficient bunching, and then we have a more efficient coherent radiation in the second ondulator. Another way to see it is actually we have 2 main emitters, ondulator 1 and ondulator 2. So it's like a Young slit phenomenon. And then we have some interference like the Young slit. Here we have the first harmonic of one ondulator and inside the interference. So you can guess that we have a larger gain, since then when we do the derivative of this spontaneous emission with these fringes, with the derivative, we will have a larger gain. So it's by replacing the first superconducting ondulator by an optical klystron that it was possible to enlarge the gain and get the first FEL. So it was the first FEL on ACO. So it was the second FEL in the world. People were kind of roaring because it was the Mady experiment was not reproduced. So people were wondering whether really this system was working. So you see here the FEL in the red, and by a change of the magnetic field of the optical klystron, we are adjusting the wavelengths. So here you see also that because of the optical klystron, we have the different fringes, and the FEL can start on 3 sublines typically. So it's a first multicolor FEL, I would say. So just to make a bit of relaxing for the presentation, to see the importance of this result, there was a paper in Le Monde and a paper in Science. So at that time it was written by not the group itself. So then if we want to go to high efficiency FEL, actually the gain bandwidth is given by the spontaneous emission bandwidth. So 1 over harmonic number and ondulator period. So the efficiency is half of it. So what we do when we saturate, when we exchange this energy, we reduce the electron beam energy. So to keep the resonant wavelengths valid, we can change the undulator parameter. So either we change slightly the undulator period or we change the undulator field. I recall you that deflection parameter is proportional to the peak field and the period. So a simple way, if you have permanent magnets undulator, is to put an angle between the arrays of magnets, and then we can change the field. So this has been used for infrared FEL at Livermore, and you see that larger peak powers could be obtained with a taper, and also with a Los Alamos electron laser, where they could get 4% efficiency. So the properties of FEL oscillators, so then I don't recall all the other FEL oscillators. I took these images on the super electron laser oscillator, and we were playing at moving the optical axis with respect to the undulator axis. And you see that you can get TEM01, 02, and so on modes. So we have the transverse mode like in a textbook of lasers. About temporal properties, as we have an optical resonator, we are close to the Fourier limit, and we can even play with it. And for instance, install a Fabry-Perot étalon inside the optical resonator to sharpen the line. And it's an experiment that we did jointly in Novosibirsk, and we could achieve 10⁻⁵ spectral line widths. So spectral range with oscillators depends on the performance of the mirrors that we are using for the optical resonator. So for a while, the smallest wavelength that has been achieved was at the Electra FEL, which was a European collaboration in Italy. And more recently, Duke FEL in US was able to go a bit below to 168 nanometer. We had also very powerful lasers like kilowatt average power on energy recovery LINAC in the United States. So with oscillators, we were a bit limited by the optics. Still, very early, in the early times, first FEL oscillator user application did start. So with infrared FEL, I put here some example about human surgery with the Vanderbilt infrared FEL in US, or photon echo, which is more basic research at Stanford FEL. In our case, on the super-echo FEL, we started we started first with time-resolved fluorescence. So at that time, there was not yet the titanium sapphire laser, so it was very convenient to use an FEL for this, to look at the coenzyme, and we could deduce the different conformational states. And then we started with PUM-PROB two-color experiments. So we used the FEL to excite a surface, and we did probe with VUV radiation from an undulator line elsewhere on the ring. So we did propagate the FEL over 80 meters, I would say, above the ring. And we could see surface photovoltaic effect, and we studied different materials. So typically the landscape is the following. We have various free electron laser oscillators around the world. The ones which are continuing to operate now are in the infrared. We have one in France, Clio. There is one in Felix, a new one which is in Berlin, and so on. So I discussed about the oscillator configuration, but you could also consider coherent harmonic generation. So then we use an external source, which wavelength is tuned to the fundamental of the undulator. And then we are doing a more efficient bunching than when we use spontaneous emission, because the laser is more intense and more coherent. And then we can, the bunching takes place also on the harmonics, and then we can extract coherent harmonics. So this has been first measured on ACO-FEL in very early times, 1 year after the oscillator, down to the VUV, reproduced on the super ACO-FEL and on many rings. We had collaboration with UV-SOR, where you could see the measurements of the improvements of the coherence with Young slits. And we played with LACT and MAX4 with its injector. But if we want to go to shorter wavelengths, we have to consider high gain FELs. So I give a bit of mathematics. So in that case, we have high density electron beam and long undulator. So a strong bunching takes place and we affect the space charge. So then we look at the evolution of the radiation with the Maxwell equation, and we make the hypothesis of slow varying envelope so that the electric field does not change much over a few undulator periods. Also, it increases over the whole undulator length. So it enables to simplify a little bit the equation. And then we look at the source term. So the source term is a current which is given by the electron beam, which is traveling in the undulator. So we have this source term which depends on this longitudinal movement of the electron. Then we can have also the density and space charge term. So for this term, we in the 1D theory, we neglect the dependence of the electronic density with a transverse position, but we have a longitudinal dependence because of the bunching. So we can introduce the space charge field, which is given here using this equation. And then we use the phase evolution that we discussed before and the energy exchange. So then if we combine this equation, we get the cubic equation, and we find different solutions, with one with an exponential growth, which is defined by the Pierce parameter, or FEL parameter, which depends on the undulator deflection parameter and Bessel function term, on the electron beam energy, and on the electronic density. So on resonance, we have these three solutions and this exponential growth of the electric field. At the start, we have the three solutions which are contributing, and we have a start which we call lethargy, where we need to have the exponential growth which becomes predominant. Then we can find that the gain bandwidth is given by the Pierce parameter, and the power at saturation is proportional to the beam power multiplied by the Pierce parameter. And saturation takes place typically after 20 gain lengths. So here is a typical calculation. So we have the startup with a lethargy. We are doing the modulation. The collective instability makes this space charge doing some bunching. Then we have the exponential gain regime. And then we have the saturation, where we can have oscillation between cyclic energy exchange, energy gain and loss. We have uncorrelated trains of radiation. So actually, this could lead to temporal and spectral distribution with spikes. So condition for having this self-amplified spontaneous emission is that the energy spread is smaller than the Pierce parameter. Otherwise, we cannot imprint the modulation. We should have an emittance smaller than the wavelengths and electron bunch longer than this for avoiding that it escapes from the electron bunch. So there were first demonstration in the infrared, and then I showed some example of SASE in the infrared. So I give an example on Clio in France, and then in US, there was a big change by changing the type of gun. So first we had a thermoionic gun, but then it was possible to use a photo injector where the laser is generating the electron and it provides a higher electron beam quality. And with such guns, it was possible to see larger amplifications, both at UCLA and Los Alamos. So then in the turn of the century at DESY in Hamburg, Germany, they started with flash for electron laser. So actually the linear accelerator was initially developed for the development of linear colliders. And it appears that the extremely high good quality needed for colliders was also beneficial for free electron lasers. So they started to get the FEL in the VUV and then going shorter in wavelengths as shown here with the developments with years. And they started to have users in the VUV on flash. So this is really a big step to show that SASE can be used and operated at short wavelengths. So then the second major effect was the advent of hard X-ray FEL, which was achieved at LCLS, Stanford, using a former linear accelerator. And so in that case, they had typically 100 meters of ondulators, and you see that saturation is achieved after 60 meters of ondulator. They worked a lot on the pre-injector part, and it took only 4 days to achieve the FEL when really they start to send to the ondulator. So this was really a spectacular result. It is really the first tunable X-ray FEL. So this is 30 years after the first FEL and 50 years after the laser discovery. So you see here the change of the wavelength of the ondulator. And now LCLS is operating also with LCLS2 with a superconducting linear accelerator. And they achieved the first result with this superconducting linear accelerator at a lower electron beam energy. So following LCLS, first X-ray FEL, we had Japan coming up with a SACLA, which is a bit specific because they have a different type of gun. So you see that they have a synchrotron radiation storage ring and SACLA FEL with a linear accelerator. Now they are even injecting the ring with this linear accelerator because they don't need it, or it's just a few some very short time to inject the ring. Then it was followed by Pohang in Korea, then Swissfel. Then in Europe, France is contributing to the European XFEL, which is in Hamburg. So it's a 3 kilometers machine. You see, using a superconducting linear accelerator, so we can have a very high repetition rate radiation. There are different series of modulator providing to different experimental stations, and you see again this exponential growth and the different lasing on the different branches. In China, they are developing a new FEL, first in soft X-ray, and then which is already lasing, and then with a superconducting linear accelerator that is expected to be commissioned within 2 years. So you see the ring and then this big FEL at high repetition rate. So if I recapitulate the evolution of SASE, we started in the 80s with saturation in the millimeter range, and we can have a kind of linear dependence with time going towards shorter wavelengths. And this is really due to the fact that we improve the quality of the electron beam over years, thanks to the development of photoinjectors. So you see here the observation of the FEL in Hamburg. It was even complicated to deal with beam dump because it's so powerful. And now I'm going to describe a bit more the properties of SASE. So actually, we have some gain guiding due to the refractive index. And it means that we can have long ondulators, and we are not so limited by the relay length. We had a good transverse properties. They have been measured, for instance, at flash with a Young sling, or we did some wavefront analysis on the CSS test accelerator in Japan. So this is good quality. From the point of view of longitudinal properties, it's another story because we have the radiation coming from uncorrelated trains of radiation. So this can lead to spiky this longitudinal and temporal distribution, as you can see here. So one way to deal with it is either to use very short electron bunch that we can have only a single spike that can develop, or we could combine an electron beam energy chap to an undulator taper, so we can manage also to have a single line. Or we could copy conventional lasers and try to do a mod-lock FEL amplifier configuration. So it's a kind of optical klystron type. So we have different segments of ondulators and different dispersive section. So we can mod-lock the radiation and get close to a single spike. So we call it improved SASE. So another way is remembering coherent harmonic generation experiments to try this in a high-gain case. So again, we use an external laser which is tuned to the undulator wavelengths, and this laser can imprint more efficiently the energy modulation to the electron beam. So we can do so, and even if we we can taper at the end to improve the efficiency. So the major experiment was done at Brookhaven in 2000, and you see here the spiky SASE and the seeded radiation, which is sharpened and with a high spectral density. Besides the fact of improving the spectral density, it also limits the intensity fluctuation and also reduces the saturation length because we are more efficient for doing the modulation. So this, you can first play with the seeding at a given wavelength, but also do high-gain harmonic generation where you do the bunching in the first undulator and then radiate on the second undulator, which is set on a harmonic on the first undulator. So there is a user facility which is operating with a seeded FEL, which is a Fermi in Italy, and it has 2 branches, and it's operated in high-gain harmonic generation. So if we want to go towards shorter wavelengths, then we need a seed at a shorter wavelength. So one idea was to use high-gain harmonics generated in gas. So this is the subject of Nobel Prize this year, given to Pierre Agostini, Ferenc Krauss, and Anne Lhuillier. So what we do is we have an intense laser, which is focused in a gas. And we have a first tunnel oscillation, which can occur, then acceleration, and recombination with emission of radiation. So Anne did study this process in CEA, and this is the first spectrum of high harmonic generation emitted in gas, and you see the spectrometer that she was using at that time. So the Nobel Prize was also given to Pierre Agostini and Ferenc Krauss because they showed that one can produce attoseconds radiation. So Pierre Agostini demonstrated that one could get attosecond pulses, and they developed a rapid reconstruction. And Ferenc Krauss group showed that it's a single attosecond pulse. So the Nobel Prize is given to the development of this attosecond science. In our case, we were interested by the fact that HEG could go to very short wavelengths. And we have set up a collaboration with the CSS test accelerator to try to seed an FEL with HEG. So we first started at rather long wavelengths at 160 nanometer. And you see here that indeed we can seed the FEL with HEG. And we have a spiky SASE and a nice seeded FEL. So this is with one undulator segment, and here with two undulator segments. And we have also these side-bands here, which are related to the synchrotron oscillation at saturation. This enables also to have nonlinear harmonics, as we can see here. So seeding with HEG indeed works. We also look at the seed intensity which is needed. So for seeded FEL, we have the following evolution. So there is, if we use HEG seeding, we have this first result on SCSS test accelerator in Japan. Then we continue in Japan with a slightly different setup for generating the HEG. And we're able to go down to 60 nanometer. So you see that going down in wavelengths, it's always time, because we did at each steps better electron beam quality. There was another collaboration with Spark in Italy, where there were multiple segments of ondulators, so we could play with this and optimize. And the shortest that has been produced is on flash, going down to 19 nanometer. Then, if we start with laser seed, we can also play by jumping from one harmonic to the other. And the question is, how far in harmonic number can we go? So we see that here in Fermi, it was possible to go down to typically harmonic 200. So this is very impressive. And there is also such an FEL in China, which is using FEL seeding. But if we want to seed in the hard X-ray, then we don't have really a seeding source. So the solution could be to use the FEL itself. And the idea is not so new, actually. It's by Feldhaus. So then he considered that one could have a series of first segments of undulator, which would produce SASE. So then the idea is to clean this SASE with a grating monochromator and make a nice pulse, while the electron are deviated in a magnetic chicane, so some dipoles, and then both are sent again in a new series of ondulators with a clean seed. Actually, it was not so easy to make a grating monochromator in the hard X-ray regime, and people from DESY came with the idea to use a diamond crystal monochromator and to operate in Bragg diffraction in transmission. So the idea is to use this as a seed and with a long series of ondulators. So the experiment was first done at LCLS. They removed one undulator segment and replaced by this Bragg crystal monochromator that you see here with the electron chicane for deviating the electrons and putting them back. And you see that they achieve a very nice self-seeded free electron laser, where again we find the characteristics of the seeded FEL, which is higher spectral density and less spikes. So self-seeding has been first demonstrated at LCLS, but also demonstrated in the soft X-ray at LCLS, then in this case with a grating, and it's a bit more complex experimentally. And then in all the different X-ray free electron lasers. So then one can modify slightly the type of diamond crystal and so on, but you see that now it's current to have a self-seeded free electron laser also in the hard X-ray. It's really important because it's improving the longitudinal coherence, and we are close to the Fourier limit in such a case. So you see with such an example that besides producing a hard X-ray FEL, we are also able to tailor the properties of the free electron laser. So then we saw the interest of having this external laser or self-seed interaction with the electron beam. So we can wonder whether if we do two electron laser interaction. So this is called the echo-enable harmonic generation. So what the idea is first to imprint the energy modulation with the first laser tuned on the first undulator segment. So as we see, we imprint this energy modulation. It's what I have explained since the beginning. Then we go into a dispersive section where we really have this modulation set. And then we send a second laser, which is imprinting a new energy modulation. So this is imprinted on a already modulated electron beam. So we can have a very sharp modulation of the electron bunch, which provides a very efficient up frequency conversion. So the emitted wavelength then is equal to an integer over the first wavelength of the first modulation, and here another integer with the second wavelength of the second modulation. This scheme presents different advantage because the bunching factor decreases very slowly with a harmonic number, which is not the case of the one laser seeding. So we could go in principle to very, very high harmonic number. And we don't need a very intense laser beam to do this modulation. So it makes the experiment simpler in a sense. And we can see, we demonstrated also that we have enhanced stability. So this is really a very important method. So first results were achieved on a test experiment in Los Angeles, in UCLA, where they demonstrated, in NLCTA in Stanford, ECHO 3 and ECHO 4. Then they could go down in harmonic and then go to harmonic 15 and harmonic 75. Then Fermi installation, so user facility where the electron beam has been operated to be stable and so on, has been modified for some period of time to be able to accommodate echo. And you see here that echo 100 was observed at Fermi, and echo was very stable for coherent harmonic generation. And then even for lasing, there were results at NLCTA in Shanghai. You see here the power growth. And the last result is from Shanghai again, where they indeed combine first an echo step to do a very efficient up frequency conversion, and then high gain harmonic generation stage, which enable to have a very intense and stable radiation. So you see that we play with a combination of the different configuration to really tailor the properties of the FEL. So then, as we have reached a stage of maturation for free electron laser, we try to tailor further the property. So the point is to control the FEL pulse duration. So I first gave an insight when I explained that radiation could be spiky, and one way was to operate with a single spike. So in that case, it's a single spike and the radiation is very short. So typically femtosecond duration. One can try to also select only a portion of the electron beam by degrading one part of the transverse electron beam, and which is called emittance spoiler. And that's a way to get a very sharp one single spike short electron bunch. Or one can play with angular striking, so by putting constraint on the angle of the radiation. What is more interesting and more advanced, I would say, is LCLS again. It's to play with the electron beam along the LINAC and to make compression of the electron beam not only with a magnetic chicane, but with a cavity at a very high frequency. So as I explained in the beginning, with a cavity, you do some bunching and you can compress. So you see that in that case, this is the type of energy distribution. And you see here the spike in current of the electron beam for this longitudinal compression with this X-band cavity. So then as the gain goes with the electron beam density, we will have gain only in this spike. And with this, they were able to reach attosecond pulses. So like with HAG. Going further, actually, with very intense electron bunches, we have also this longitudinal space charge that we can do naturally this spike. So indeed, now it's no more necessary to have an X-band linear section, but we can just play with this longitudinal space charge and get this spike in current for having sub-femtosecond pulses. So the latest result is that it was possible to achieve 400 attosecond, 200 attosecond pulses, and to start exploring attosecond science with X-ray FELs with high power and tunability. So you see that this attosecond science that was introduced by these Nobel Prizes in HAG created some inspiration for FEL community to develop also attosecond pulsars and to try to continue this attosecond science with the FELs. So if I continue with advanced properties, so polarization control, this is kind of simple because we can play with the polarization with ondulator type. If we have a planar ondulator, we have the electric field which is emitted in the plane of the trajectory, so horizontally, horizontal polarization. Whereas if we have a helical ondulator, we have a vertical and horizontal field. Then we have a helical trajectory and we have a circular polarization. So one way is to play between the polarization of the ondulator. As we have a series of ondulator, we have an extended source in longitudinal. So in fact, it is better to alternate ondulators with different polarization to create the polarization of the FEL. So here I show an experiment at Fermi where they used a cross-circular polarized ondulator to generate polarization. With FEL, as I explained about the phase of the FEL, and this is very interesting because we can also develop angular orbital momentum and vortices in FEL by playing with the phase, and this we can do either using helical ondulator or putting a spiral zone plate on the light. And it's still an exploration because people are still considering really how they could use this angular orbital momentum FEL light, for instance, for magnetism, that they could see directly some phenomenon sensible to this. There are a lot of development of this type of sources with conventional laser, and this can be also explored with FEL sources. So if I continue with advanced properties, I mentioned about the ACO FEL, which is multicolor FEL, but it's also interesting to do multicolor FEL in the X-ray range. If one wants to do pump-probe to color experiment, then it can use an FEL of one wavelength and an FEL on another wavelength and play to excite and probe a system. As a chicane was installed for self-seeding, actually we have two series of ondulators, here and here, and the chicane. Then we don't use a monochromator, but we just set the first ondulators to a given wavelength and the second series of ondulator to another wavelength. And if we have sufficient margin in ondulator lengths, we can lace on the two wavelengths with the different segments of ondulator. And you see here that then we have this FEL with two photon energies. So this can be done with different series of ondulators tuned at different wavelengths, but you can also do it by using two electron bunches of different electron energies. Since the wavelength depends also on the energy of the electron beam, then you can have two FELs at different energies coming from the two different bunches. Providing multicolor FEL with echo is very simple as well. So I put the example of Fermi, for instance. And here with oscillators, it has been developed also at Clio with two ondulator segments tuned at different wavelengths. And for seeded FEL, then you can play also with electron beam dynamics. And you have a natural effect of splitting because you do the modulation. So here you have the wavelengths versus the longitudinal position. And you see that since we have this energy exchange, then the FEL is searching some fresh electrons, which are not where the electron, the energy spread is not so much enhanced. So they go on the side of the bunch, and we have this splitting, which can be used to do a two-color FEL. So to control it better, the way is to chirp the seed, and then we can control better this pulse splitting, and it's what has been done at Fermi. So here with Fermi, we can use the same idea as twin bunches of different electron beam energy, and then we get two-color FEL. So you see that we can play different tricks to really make the FEL property as requested by the users, and it's really developed at Fermi, where they try to really answer specific demands of the users. So then, if we come back to oscillators, what could we do again in the X-ray range? So in the past, there have been this idea of a regen amplifier for electron laser. So again, taking an idea from conventional lasers going to FEL. So to go on to make a few turns to amplify the FEL. So this has been done in Los Alamos here. And then the question, can we do it on a ring or on a LIDAC? And then the idea is to use specific optics, which are now not so bad, and do several passes to enhance the FEL power. So there has been an experiment at Stanford where they could measure the terms in an empty cavity. So this is a first result already. And there is some work going along with this. So now, if I recapitulate with the development of free electron laser, so what I explain is first FEL oscillators in the infrared and then in the visible, which was really the start with accelerators of not high electron beam quality. Then SASE, high gain studies and SASE ideas were developed at the very beginning of FEL, and first demonstration were really at long wavelengths because the gain was very low. And step by step, with the improvement of electron beam quality, one could go down in wavelengths. So you see here in green that we have development of many FEL oscillators versus time, typically in the infrared UV and VUV. So last century was really the century of FEL oscillators and user application of these FEL oscillators. The application of these FEL oscillators were really important to show that the field was really of interest, and it was the beginning. Different sources were explored, like HEG, FEL, last century. When people came with the idea of doing SASE at very short wavelengths, like for LCLS, everybody was wondering whether really this could work. So there was a major step with a flash in 2005, starting in the VUV with users. And then 2009 LCLS, first X-ray FEL, other X-ray FEL in the SASE, and then self-seeded FELs in the soft and hard X-ray. So if I recapitulate the properties, we have tunability, which is very easy with the ondulator or with the electron beam energy. And this is really a nice property of the FEL. Tunability is very simple. Polarization is simple. It's the technology of the ondulator. Spatial coherence, it depends on the electron beam emittance, electron beam quality. And here we benefited from the development of accelerator for linear colliders. So you see again that everything is linked. John Mady took ideas from lasers. We take advantage of technology development from high energy physics community. So really, you have to be kind of aware of the development in different fields, and sometimes it gives ideas. So temporal coherence, I spent some time on this. It's kind of tricky because with SSE, you have these uncorrelated trains which emit spiky structure, but we can deal with it with different schemes. Short pulses, so femtoseconds, and now attoseconds. So actually, I would add to the words of Charlie Braro that he said that we had a very nice gain medium. I would say it's an agile gain medium, but because we can play and manipulate and control this gain medium to have advanced properties for users. So here is typically a panorama of VUV, X-ray, FEL sources. And if we look at the peak brightness, it is the number of photons by 6D phase space. You see that free electron laser overpass synchrotron radiation sources by several orders of magnitude due to the fact that they have very short pulses and a very high level of coherence. So, of course, this X-ray free electron laser unable to explore new physics. And one domain of exploration is X-ray nonlinear optics. And here I show one of the first examples which has been achieved on LCLS. It's to look at the response to an ultra-intense X-ray ray of the neon atom. And or we can also look at atomic inner shell X-ray laser at 1.4 nanometer pumped with by an X-ray FEL. So this is really a new domain that cannot be explored with another source than the X-ray FEL. Then there has been a lot of experiments of coherent imaging with nano resolution. So one can do snapshots of frozen objects, so tiny fragile crystal or single particles, before destruction, because the power is so intense that it can destroy the sample. But we have sufficient time to get the information and analyze it. So here is the study for mimivirus. Actually, is a big virus. So this enables to have new information for virology, for instance. So here, do imaging of living cells. So this is with the high rate FEL. So this type of application is now taken a bit over also with upgrades of synchrotron light source with smaller emitters. So it's not some of this type of application can be done with other type of accelerator light sources. And the third category of experiments is what we call molecular movie. So it's pump probe experiment. And one can, for instance, study ultra-fast optical demagnetization or electron transfer in solvated molecular assemblies. So there are large varieties of application and many groups which gather in teams to exploit these FELs. So then I will finish this lecture by what are the new paths of exploration and what we are looking at. So I think I showed you that there has been a spectacular progresses of electron laser field along these 50 years from the first FEL demonstration to now this advent of this high intensity X-ray FELs and with a variety of application. So what I am working now is is to try to use advanced accelerator concepts and laser plasma acceleration. So it's a community which is emerging and they have a new the results of beam quality. And the question is whether this new type of accelerator is suitable to drive an FEL, or we can say whether FEL could qualify this type of new accelerator. So laser plasma acceleration was proposed in 1979 by Tajima and Dawson. And they consider an intense laser focus on a gas jet or cell or capillary. And this laser, there is a laser wake field which is excited by the laser, which is in resonance with the plasma, which induces a perturbation of the electron density and then creates a very strong accelerator field, as you can see here, in the linear regime or nonlinear regime. So in the nonlinear regime, plasma electrons are blown out, and we have a bubble with electron behind the laser pulse. So it's we can reach a giga-electron volt per meter, so this could provide a very compact accelerator. So there are some limiting process, the laser diffraction, the dephasing between the electron and plasma wave, again, question of velocity, laser depletion, and electron beam loading. So the laser plasma acceleration development is the following. So after the proposition of the concept by Tajima and Dawson, so which came from the invention of the laser as well, such as the FEL. There was first experiment with relativistic plasma excitation and self-modulation laser wake field, but with very preliminary result. Then a big change for the laser was the invention of chirp pulse amplification by Donna Strickland and Gerard Mourou, which enabled to have high power laser. And then came 3 main results from 3 different groups published in Nature, and the volume was called Dream Beam. So what they could have a larger electric field and a better electron beam quality. So I say better electron beam quality, it was still quite far for what is obtained on conventional accelerators. So at Rutherford Appleton Lab, they could get 50 to 80 MeV and an energy spread on the peak of 3%. At Berkeley, 2% energy spread on the peak at 86 MeV and peak current of 10 kiloamps. And at Laboratoire d'Optique Appliquée in Palaiseau, 170 MeV and 24% energy spread, 0.5 nanocoulomb. So they call these beams monochromatic electron beams. But for us, from conventional accelerator and linear accelerator, we have an energy spread of 10 minus 4, 0.01%. So there are orders of magnitude in terms of energy spread. And if energy spread is too large, the energy modulation can be washed out by this natural energy spread. Still, soon after these major results, came the idea whether LPA beam could be used to drive a free electron laser. So was considered a 1 petawatt laser with 5 femtoseconds pulse duration, 1.7 GeV, and 0.1% energy spread, so much smaller than one has been achieved experimentally. So, and us at SOLEIL, we started to think about whether we could try an experiment together with Laboratoire d'Optique Appliquée. So it's a coccinelle first thoughts in 2011. So there was some new result at Berkeley and LOA, Livermore, and I will go along the question of what we do need for driving the FEL. So in more details, in the paper about the calculation for whether we could do an FEL with this 1 petawatt laser. You have here the parameter, which is the emittance, the energy spread. So the question is really, is LPA electron beam quality sufficient? And FEL application could qualify this LPA. So of course, the argument of capacity was raised. To me, first, it's important to demonstrate that you can do it and you can do an FEL of good quality. So personally, it's a second level argument about the capacity. So I will review the characteristics of the LPA to see whether really we can try to do something. So from the point of view of the electron beam energy, there have been some progress after these dream beam papers. Berkeley could go first to 0.5 GeV and then 1 GeV, Livermore to 1.4 GeV, Texas University 2 GeV, then Berkeley 4 and 8 GeV, and Texas University 10 GeV. So for the electron beam energy, it's okay. Then energy spread. So energy spread, it's a bit tricky. So the way to control the energy spread is to play with the injection and the acceleration, because in laser plasma acceleration, you have two processes. You have to inject the electrons in the accelerating field, and you have to control the acceleration. So one way, which has been demonstrated at LOA, is to use two lasers separated, one for the injection and one for the electrons. And then they could get 2% level of energy spread. This is working, but it's a bit tricky to set experimentally. Or you could play with the injection scheme itself and play with the plasma density and the types of ionization that you have. So this has been done. And you can assist with a shock to really shape the plasma density. So you get several % of energy spread. Or you can also do some energy chirp, as has been done in China, in Xiom, and they reach a very low energy spread of 0.4% or 1.2%. So this is interesting to consider. Then in terms of charge, so I told you that electronic density is important to have a gain. So what is the charge that can be achieved? So I give here two examples. In Germany. So Helmholtz-Zentrum, Dresden-Rosendorf, where you see that typically 100 picocoulomb charge can be achieved, or Munich in Cala, where you could go to hundreds of picocoulomb with a more intense laser. About electron bunches, they are very short. They are typically femtoseconds or 10 femtoseconds bunch duration. So this is nice to have a large peak current. And emittance is okay. It's typically small. Still, we will see that divergence is large and the size is very small. So this might be a bit tricky. So if I recapitulate the typical parameters that has been achieved, you see on this graph the charge, the energy spread, and divergence. So there have been a significant progress achieved since this drift beam. Still, we have strongly diverging beams, 1 millirad. We still have a large relative energy spread. And if I compare to this high repetition rate LINAC, driving a new generation of X-ray FEL, it's still low, but for trying to explore what could be done with LPA, it's fine. So if we think we want to try something, we can try to improve the electron beam quality and handle it through the transport to the undulator. So about the transverse phase space. So if I do compare conventional accelerator and laser plasma accelerator. A conventional accelerator, we have typically 1 microradian divergence and 1 millimeter size. While for an LPA, we have 1 millimeter divergence. And on accelerators, we could have chromatic effects that we could have an emittance growth, which is scaling as the square of the energy, the divergence, and linearly with the energy spread. So on conventional accelerator, we do not suffer so much from chromatic effects because energy spread is low and divergence is low. But on LPA, we can, if we don't do anything, just by letting the electron beam going in free space, we will have an emittance blow up thanks to this chromatic effect. So what we have to do is refocus strongly the electrons right after the generation and the acceleration of the electrons. So this can be done with permanent quadrupoles or with variable gradient permanent quadrupoles, permanent magnet quadrupoles, as we have developed at SOLEIL for such an application. So you see here we have a central quadrupole and then rotating magnets which enable to vary the quadrupole field, so the focusing field, it's like a lens, magnetic lens, by 50%. Or we can do this also with a plasma system, with a plasma lens, which could be passive or active by applying a magnetic field. So with this, we can control the divergence. For the longitudinal phase space, typically it's rare that we start with 0.1% energy spread. It's only the Chinese experiment for the moment. So one way is to go along a decompression chicane. So contrary to linear accelerator where we have to compress the electron beam, here we go along different dipoles, different making magnets, and electrons of different energies will have different trajectories, so that we introduce an energy position correlation, and we can write what is the decompression factor. This is typically like with gratings. And then we can sort in energy the electrons. We can even take further advantage of this energy position correlation by applying a chromatic matching. So then we have to focus the electrons inside the undulator, but which counts is the slice of the electron, which is interacting with the wavelengths. So we can focus in each slice at the proper energy in synchronization with the progression of the optical wave. And then you see that we can have a larger intensity. There is another way to deal with the energy spread is to put some correlation of the magnetic field with the horizontal position. But then it's a bit tricky because if we have pulse-to-pulse fluctuation, it's not working maybe so easily. So it's what we have done for our test experiment with Laboratoire d'Optique Appliquée, coccinelle. So we have the intense laser focus in a gas jet or gas cell. Then we have a triplet of strong quadruples of variable gradient located 5 centimeters away from the source so that we handle the divergence of the electron beam. Then we go along the chicane to reduce the slice energy spread. So we reduce typically by a factor of 10. Then we have a second set of electromagnetic quadrupole to adjust the chromatic matching for the undulator, and then we have some spectrometer to look at the radiation. So first, we were able to transport properly the beam. So we look at the beam at different locations, and we have the measurements which are in agreement with the modeling. So for the modeling, we take the parameters which were measured at the source. So you see here a picture of the line installed at LOA. So there were several developments for first looking at undulator spontaneous emission, which is undulator radiation, because it's the first step to get an FEL. So there have been first measurements here. Then at LOA with the first undulator. Then, so going down in wavelengths, 18 nanometers, here in England, 224 nanometer, here in Germany, 13 nanometer. And on coccinelle, what we were able to do is, since we had a chicane to control the energy spread, we can put a slit and then select a given energy spread. And then in such a way, we are controlling the bandwidth of the undulator radiation by controlling the energy spread and limiting the energy spread, the inhomogeneous bandwidth. So we were able to have a few percent bandwidth of undulator radiation. So then the question is, can we get the FEL? And the first to get the FEL is SIOM, and it's normal, I would say, because they had the best electron beam quality with this sub% energy spread level. So what they use again, quadruple triplet. There is no way to do without it, because otherwise you have the chromatic growth of the emittance right after the source. But in their case, they don't need the magnetic chicane, since they have already a very low energy spread. So they operate with 0.5 energy spread, 500 MeV beam, 30 picocoulomb, and a very small divergence. And then they have 3 segments of ondulators. So you see, and they operate in a SSE regime. So you see here the FEL wavelengths, and then here the growth. So here is first segment of undulator, second segment of undulator, and they could have 2 orders of magnitude of amplification at 27 nanometer with a third undulator. So this is a very important result for the community, because it's the first LPA-driven FEL. Of course, it's not at all stable. And what they say in their paper, the high quality from LWFA, laser wake field acceleration, effective guiding in the undulator, so control with the transport line, are of crucial importance to the realization of FEL. So it's the same that what I said also with conventional laser. You have really to control the electron beam and have a high quality electron beam. So with the experiment in LOA, actually we tried for the FEL, but the electron beam parameters were a bit too far from what was needed. So we considered the beam parameters from the Dresden experiment, and they made some new measurements. And finally, we saw that we could demonstrate the FEL. So we transported the line. So actually, it's a full truck of equipment. We changed we took a new server. We tested each separated equipment with its cables before putting in boxes, and then we spent like one long week to install and align. So you see here the permanent magnet quadruples, which are installed in the chamber of laser plasma acceleration. So we have special copper cables for good vacuum, for the connections on the vacuum. You see here the in-vacuum ondulator. So the magnets are inside the vacuum so that we can close the gap to 4 millimeters to have a larger field. So this is typical ondulators that we have at SOLEIL. This has quadruples, which are used to do the supermatching. Here the dipoles of the chicane, and the LPA chamber is over there. We operate, so the colleagues of Dresden are operating with a 100 terawatt Draco laser, with 2.1 joule on target. And you see here the electron beam quality. So actually, they have a passive plasma lens, which enables to have a rather low divergence. So typically below 1 millirad. You see here the electron beam energy and the stability in energy. So the shot-to-shot reproducibility of the energy is not perfect, but it's not so bad. And this is the trend of all the data that we took for the FEL shift. So you see that the electron beam energy is still rather stable and the divergence. So then we could do the transport very rapidly. So we are starting with a smaller divergence. So we have a nice spot without the quadruples, and then we focus. So we have a smaller spot and proper control in the chicane and at the dipole dump. So here we have the undulator radiation. So it's the wavelengths versus the vertical position along on the monochromator. So we have this gamma square theta square term. So it is this parabolic shape of undulator radiation. So it's a proper undulator radiation. Spontaneous emission is fine. And then we could, so we are operating in a seeded configuration. So the seed is prepared from the TISAF laser itself. It's spectrally filtered and spatially filtered. So we do the spectral overlap on the monochromator, the temporal overlap with a phase gastric camera, and spatial overlap by looking at both seed and synchrotron radiation along the undulator. And we could get the FEL signal during the first delay scan. So the FEL is this tiny red-shifted light, and this is the seed. And actually, it is red-shifted because we have a chirp electron beam in the chicane, which leads to an elongation of the modulation, FEL modulation. So we are red-shifted, which is very convenient to see the FEL. So we can see that indeed we have the FEL when we measure the seed alone, the spontaneous emission alone, and then the FEL. Compare with the modeling. We have the quadratic charge dependence, which is a signature of coherent emission. The dependence with the gap, and the dependence with the delay, which enables to tune the FEL. We have fringes on the side of the line, which results from the interference of the seed and the coherent emission, which was expected. And it is a signature of the phase locking and the evidence of the temporal coherence of the seeded FEL. So next, we have to improve the electron beam quality and go with a longer undulator of smaller periods. So with calculation, we could go to shorter wavelengths. There are some preliminary results from Berkeley as well now in SASE. And to conclude for this part, we have achieved a seeded FEL with LPA 11 years after the start of the work. And there is a SASE result at SIOM. Still, the further improvement of the electron beam quality is needed to be able to obtain a stable control LPA to be able to start with a FEL pilot user experiment. There is also a big project, Apraxia, which is on the S3 roadmap. So let's see. So this could enable to have a more compact tabletop FEL and maybe provide unique properties of terawatt attosecond and combining petawatt class laser with an FEL. So then to conclude about the evolution of FEL, it's just to recapitulate what we have seen, the invention of the laser, the first FEL, advent of X-ray FEL, and first results of laser plasma FELs. And I wanted just to conclude that FEL is the most intense laser in the X-ray range, that we have an agile gain medium that enables to control and manipulate the system to have advanced properties. And the new accelerator concepts applied to FEL are still in the childhood. Thank you for your attention.